Hi class, so today we are going to talk about the science of sauces, which are what make or break a dish. Every chef knows that sauce is important to the dish that you are making, and we are going to talk about some of the classic sauces and also how they are formed on a chemical level. So the basics are that sauces are a mixture. They're a combination of a solute and a solvent. And there are two types of mixtures. We have a homogeneous mixture and a heterogeneous mixture. Homogeneous mixtures are also known as a solution since it is of one type of consistency and texture. Now, the basics are that we dissolve these particles evenly throughout a medium, which they become dispersed, and as they disperse, they impede the free movement of water, which gives us the appearance of texture or consistency. So it makes things appear thicker and slows the free-flowing viscosity of whatever the water is. Now, there are mother sauces, which come from classic French culinary technique. And now let's hear from a Frenchman what those are.
All right, to go nicely with your meal and your meat and your veggies, you can have different sauce and nappage with sauce allemande, sauce béchamel, sauce veloutée, sauce espagnole. That's very good.
So they also added to the mother sauces. Now, the current list of mother sauces also include a sauce tomate, a tomato sauce, and a hollandaise, which is a emulsified sauce. And we will talk about the different kinds of thickeners that there can be. So molecular, these are thickeners in which there is a gel. They tend to be translucent. Particular, these are sauces in which a particle or a puree actually impedes the movement of water, giving the sauce its thickness. An emulsion, which are cloudy, creamy sauces of a homogeneous, stable mixture. We know about this. And an air sauce. These tend to be foams, light and stiff, and they tend to be chilled. So just some general thoughts about those. Now, a lot of sauces, they use many different thickeners, not just one or the other, so they can have multiple thickeners at play. Obviously, when we're talking in our quizzes and when we're testing, we're looking for general, what is the majority thickener here, and the kind of thickener used depends on the sauce and the materials that are used. And some sauces can even appear solid, even though they are not fully solid. So if you think of something like ice cream is technically a sauce, and it appears solid, though it is mostly air. And we'll talk about that as well. So the influence of consistency when it comes to flavor. This is a chef's trick and one of those things that I always keep in my back pocket. Thickeners will reduce the flavor intensity the same way a high fat content will also influence flavor intensity, and you need to counteract that with the addition of more salt and strong flavors. So the thicker a sauce is, the more salt you need, because it will reduce your perception of saltiness. Because the thickeners will bind to these flavorful molecules and keep them trapped. Now, let's talk about the different kinds of thickeners. So the first one we're going to talk about are molecular thickeners, and these are gels. They're stable once they set. They don't block light rays, so they're usually translucent or clear, and they have a jelly-like consistency. And they can move between hot and cold temperatures without losing its ability to thicken again. So for instance, we learned in our meat lecture about collagen and how that is at play in bone broth and ramen broth. And as you know, that can cool down and will set into a gel due to the gelatin, which is a molecular thickener. But once we reheat it, it will liquefy again. Now in these, there are these single molecules that act as the thickening agents. Gelatin, a carbohydrate, pectin, and they do require heat to improve the thickening process. So these molecules, usually protein-based, have to undergo heat, which is going to force them to denature and then coagulate. And as they cool, they will set. And they won't separate out after they set. And generally, they don't block the light, they're translucent. So we're looking for proteins that have denatured and barely coagulated, not fully curdled, obviously. Now, the dissolved molecules of plant starch or animal gelatin, they tangle with each other and they impede the flow of the liquid. So if we take a look at these images here, we can see that these molecules are creating a web. And what happens is the water molecules and the other free-flowing molecules dissolved in the water, dispersed in there, get trapped in these nets. And as they cool down, they begin to solidify, and they literally keep those molecules from moving, impeding their movement, and that gives us the consistency of a thicker sauce. So if we're talking about a jello or jam, that's what happens here. So the important thing is you want to make sure that whatever you're doing with this sauce, you have a lot of flavor dissolved in your water to begin with, because that's going to ultimately give flavor to your dish. Gelatin, we talked about, is a very long and flexible protein, and heat breaks these bonds, which then denatures them. And the collagen also has many medical uses, and it can have up to 1,000 amino acids in a single gelatin molecule. So it's very, very strong, long molecule. It's used like glue. It can be used for sutures, to close wounds. There's a lot of use of collagen and gelatin, both in food and in biology within medical use as well. And again, we can control their thickness or thinness using thermoregulation, or the application of heat and coolness. So if we want a thicker sauce, if we are going for something like an aspic, which is a set gelatin, it's served chilled. So this way you can actually slice it. That would be something that like surrounds the product head cheese. Or if we want something more free-flowing like a ramen, we're obviously going to serve it piping hot. So albumin is another protein found in egg white, milk, blood, and other animal and plant tissues that can also thicken sauces. Cheese and yogurt, the casein, which is a milk protein found in dairy products, can also thicken sauces. So if you are making, let's say, a sag paneer and want to thicken it with either a cashew cream or a cream or yogurt, you would use that to thicken a sauce as well. And it's the casein milk protein in there that does that job. So when coagulation goes too far, if you are using a molecular thickener and coagulation goes too far, what you can do is actually blend it, which will break up those proteins, strain it to move out any curdled proteins and re-thicken it. And then you can also add a secondary thickener like flour or starch, which can prevent some of those proteins from fully coagulating and clumping again. And always whenever we're adding a thickener to a sauce, we add a little bit of the hot sauce into the thickener first and then into the full sauce. This is because you don't want to raise the temperature on these proteins so extremely right off the bat. If we give them a little bit more time to slowly raise their temperature, what's going to end up happening is they will gently unfold instead of unfolding, coagulating, and curdling right away and leading to a lumpy sauce. So thermoregulation, or the temperature control, is very important. And now, so commercial gelatin is made of 3% gelatin, and you can see here the collagen as it's a liquid and as it's a solid, and how it sets up in different states. We can see how the proteins form from a liquid gel to a solid gel, and again, they're just trapping those water molecules in there, impeding their movement and creating more of a cell, a sauce. Now, one of the types of food thickeners that we also come across very frequently as a food additive are gums. They're bland in taste, odorless, and tasteless. And a lot of these come from seaweed. So we have agar-agar, carrageenan, alginates, gellan gum. Gellan gum is a polysaccharide secreted by bacterium, whereas the other three listed, agar-agar, carrageenan, and alginates, are all polysaccharides which come from different kinds of seaweeds. And they're really great at creating a homogeneous suspension. So if you look at a lot of sauces in the supermarket, you'll see that they contain one or more of these different gums, and what they do is they give the appearance of a thicker consistency within the sauce. One of another cool thing that was invented is spherification. So Farion Adria of the restaurant El Bulli in Spain invented the concept of using a technique that would have a chemical reaction between sodium alginate and calcium chloride. So as sodium alginate comes into contact with calcium chloride, a thin gel skin is formed. And pharmaceutical companies had been using this for years to create gel caps. So what they would do is they would encapsulate in this gel using sodium alginate and calcium chloride the medicine that you would be taking, and you would eat it and it would dissolve in your body as it heated up, because obviously molecular gels are going to be dissolved at a higher heat. So the internal body temperature that we provide was enough for it to dissolve, and the medicine would be released into your system. So the same way that had been used in medicine for a long time, Adrian Ferrar took this concept and applied it to food. So he said, what if we take something really flavorful and we encapsulate it in a gel? So he created the first spherification, which was an olive. So he made an olive juice, which was a concentrated olive flavor, and then encapsulated it in this gel and spherified it and served it in a jar of olive oil, and people were shocked and awed at the texture. So it had all the flavor of an olive, but it had the texture of like a popping juice candy. So it's very popular still today within molecular gastronomy. If you're still looking for a term paper topic, which I hope you're not, but should you be, molecular gastronomy would definitely be one that you could explore the roots of and the modern use of. Molecular carbohydrate thickeners. Some other ones that are commonly used are flour and starches. So the starch, the amylose and amyloipectin within different food products are also used as thickeners. So amylose is predominant in potatoes. It is linear. It has a straight line structure, not quite as much thickening power. So you can use potato starch or just actually ground up potatoes will help to thicken. Whereas amyloipectin is derived from wheat and corn. It has the same number of glucose molecules, but it has a branch structure, making it a much stronger and more effective thickener. And we use this obviously with things like a roux. If we're making a sauce, it can be used in that construct as well, and that does have molecular thickening properties. Jams, again, another molecularly thickened sauce or jelly. So what we're doing in these are creating a colloidal system in which the fruit's watery juice is trapped in a web of the pectin molecules. Pectin is a polysaccharide from the unripened skin of fruit. So it is found in certain fruits and also can be applied directly. It does need sugar in order to activate because the sugar decreases the water content, and adding an acid will also increase the positively charged molecules, which then neutralize the negative charges on the pectin, so pectin can bond with itself. So these two things are critical when making jams, so controlling the pH and also ensuring that there is a certain level of sugar available that is important for the gelling of the pectin. So, which thickener should we be using? I mean, there's a lot of molecular thickeners. I think of all the thickeners we're going to discuss today, the most are molecular. So starch thickeners are great. They give food a transparent, glistening sheen. Cornstarch is the best choice for thickening dairy-based sauces. It should never be used in any sort of frozen application. If you do plan to freeze a dish, tapioca starch or arrowroot are great thickeners. Arrowroot will thicken an acidic liquid. It's also the most neutral tasting of the starch thickeners, and tapioca will thicken quickly at a relatively low temperature. So should you be in a bind and really need to thicken something quickly, it doesn't require the same thermoregulation that other starch-based thickeners do. So let's take a pause here and recap what we just learned about molecular thickeners. So what's one thing you learned about molecular-based thickeners or sauces in general that you didn't know before? Great. Now, I'm going to make jam. What are some of the critical components to jam making? What do I need to ensure in order to have a properly set gel with pectin? I'm going to use pectin. So what do I need to ensure I control in the process? That's right. We need to control the pH, and we need to control the amount of sugars that pectin can bond with itself, and we can neutralize its charge, and then it can be a properly set gel. Otherwise, it'll be very thin. Now, I have a bowl of ramen that has cooled down and has set into a kind of jelly. Is it bad? What can I do to serve that ramen at a liquid? How can I serve it as a liquid? Great. And finally, how do we know that something is a molecularly thickened sauce? What are some of the cues for a molecularly thickened sauce? Yeah, it's going to be clear, it's transparent, it is cooled, thickened in a cooler temperature, and thinned out or more free-flowing in a warmer temperature. Those are going to be some of the cues that we're dealing with a molecularly thickened sauce, and it's definitely a homogeneous sauce. Okay, did you take a quick break? Let's get back to it. We have a few more sauces to go, and then I will lovingly release you to the rest of your week. So particulate thickeners. Particulate thickeners are usually opaque. They're best served warm or hot. And the key to a particulate thickener is that you can see the particles. You can see what is impeding the movement of water. So we're talking about large molecules that are impeding the movement of the water. So these are like giant barriers for the water movement. We're not trapping them in a net or anything like that. They are heterogeneous and they will separate over time, especially as they're cooled. If you've ever left a sauce in, let's say mashed potatoes in the fridge and saw like a water kind of separate from it, it's because that's a particulate thickened sauce. And it is separating as it cools. Now, another particulate thickener is a roux. A roux is a combination of flour and fat cooked together, used to thicken sauces. It can also be made with butter, lard, vegetable oil, depending on the cuisine. And it's in 3 of the mother sauces of classical French cooking, a bechamel, a velouté, and an espagnole sauce. And depending on how we cook it, we're going to end up with different properties. So being that a roux is made of a fat and flour, as the flour made of starch and protein continues to be cooked, what kind of reaction are we going to see? Let's take a look at these pictures. You see it going from light to dark. Now, what's happening here when it's light is a lot of these molecules are absorbing the liquid and they're beginning to gelate. That starch is gelating, and it's going to provide more thickening. Now, as we move over here to the very dark one, what reaction are we witnessing here? We're talking about flour over high heat, flour made of starch and protein, starches which break down into sugars. That should be your key. So what reaction do we have here? That's right, the Maillard reaction. So we're creating these large brown polymers that have a very intense, savory taste. And if we cook a roux all the way to the darker end, we're not using it at that point for thickening because the starches will have been fully broken down. They're going to no longer gelate. But what we're using that for is flavor. So if you're making a gumbo or a gravy, you want to make a big pot of dark roux, which is going to add a lot of the flavor into your sauce. So as you think about the holidays and you think about making, dark brown sauces, we're really talking about a roux. Now in these particulate thickeners, the starches will swell before they gel. So we are using a lot of same starches that we use in our molecular thickeners, but we're talking about using them before they reach the gelation range. So they will absorb water until they reach their maximum thickness. Then they'll begin leaking amylose and amyopectin molecules. And those form that fishnet, like the gelation, that entraps the pockets of water and blocks the movement of these big water molecules. So like we said, many sauces are not just one type of thickener, but they can be many types of thickeners altogether. Now, you have to be careful not to overdo it because we want this thick mesh with these large granules. If you overcook them, what ends up happening is you destroy the sponges. So these starch molecules fully gelate, and as they do, they break down, and then you only have small granules, and your sauce actually becomes thinned out again. We also use plant cell fragments, which are visible to the naked eye, to thicken a sauce. So for instance, if we have a sauce that is a creamy soup, we can use vegetable particulate in order to thicken that soup. So you can take butternuts and you can roast them and you can puree them with a flavorful liquid and end up with a very creamy sauce, but as it cools down, it will begin to separate. And here's an example of that, as the water and oil will separate as the product cools. Now, tomato sauce is very interesting. You can either cook a tomato sauce very quickly or you can cook it for a very long time. And there's a chemical reason for this. 2/3 of the flavorful sugars and organic acid in tomato sauce need to break down. So 20% of the content of a tomato is the cell wall, which are long carbohydrates, 10% cellulose, 5% pectin, and 5% hemicellulose. And as we know, all of these things will gelate. So as they release the pectin and cellulose, they break down the cell walls and they thicken the puree. This can be done very quickly, but as you continue to cook it, the puree will then become thinner and needs to be further gelation in order to break down and become thick again. All right, so we talked about particulate thickeners. Let's recap. What is an example of a particulate thickener? Can you give me one example of something that could be used as a particulate thickener? Excellent. I'll read all your answers, and as long as it's reasonably a reasonable guess, you will get full credit. And particulate thickeners, we can tell that there's a particulate thickener. What are some of the cues that we are dealing with a particulate thickener? That's right, we can physically see them. They're visible to the naked eye. It is a large chunk of material blocking the movement of the water, and that can be a potato, it can be vegetable, it can be animal, anything that is going to stop the free flow of water. Now, when we talk about a roux, if we're creating a dark roux, why would we use a dark roux? What is the food application? What does it give us? Umami, savory flavor. Yeah, because we're developing the Maillard reaction there in that dark roux. Still with me? 2 more sauces and then we'll be done. This one we're gonna go pretty quick because we already know what an emulsification is. It's a stable, homogeneous mixture between polar and non-polar substances. It can be oil and water or water and oil, but most sauces are oil and water systems. They're creamy. They're usually served room temp or slightly warm. Heat can break an emulsion, so it's never served hot. And it's always going to be a homogeneous and stable mixture. Now, anytime you see a bottle of salad dressing that looks like a vinaigrette, unless there's an emulsifier there, they're definitely using a secondary molecular thickener, like some of the gums we discussed earlier, to keep it as a stable solution. And here, I love seeing the stages of making mayonnaise visualized through a light microscope. So you can see as the fat droplets beat up and the emulsifiers surround them, there's a very tightly packed, semi-solid emulsion of small droplets to make that mayonnaise, which has an almost thick, solid consistency to it. And the final sauce we're going to discuss today are foams. So foams are sauces thickened with air. These are things like ice cream. It can be a literal foam, which is some things that decorate very fancy dishes. They're fragile and evanescent, and they have very different densities, so the air bubbles rise while the water sinks. They're usually served cold. If they're served warm, there's almost always a secondary thickener, which is going to be molecular. We can tell that they're foam because we can see the air bubbles, and they can be dried through slow dehydration, as in the process of astronaut ice cream, dehydrated ice cream. Now, tiny spheres act much like the solid food particles do, interflowing with the flow of the liquid. So the same way in a particular thickened sauce, we can see the particles thickening the sauce. In an foam, we can see the air bubbles used to thicken the sauce. And when we talk about one of my favorite air thickened sauces, and probably yours, ice cream, the amount of air in an ice cream product is called overrun. And it can go anywhere from 10% to 45 or even 75% overrun. And what this means is the amount of air that's pumped into the base is going to create something either gelato, ice cream, or soft serve. The only difference between those products is the amount of air. So if we take a look at whipped cream, there's 2 things happening here. First, we are resolubilizing the fat. So the fat droplets are resolubilized, turning them into like a sheath that protects and holds those air bubbles and causes a net that traps them and holds them there. We always want to whip our cream until it is just beginning to look solid and not keep going, or we move into a clotted cream, which then moves further into butter, where we are taking all the air out and really fully resolubilizing the fat and rearranging those particles into a different substrate. And I love seeing this image right here under the electron microscope. We can see how the fat globules fully resolubilize to hold those air pockets and provide a very stable substance, whipped cream, over time. Now, last recap. What did we learn about emulsification? What is an emulsification? Great. Can emulsifications be served hot or cold? Yeah, they're best served chilled or just warm, but never hot because they'll break. And finally, how can we tell that something is an emulsification? What are some of the visual cues if we look at it? Right. It's going to be creamy, cloudy, opaque, served chilled or just barely warm. And there's definitely a fat at play. So it's going to have a good quantity of a lipid in addition to the water or acid. Now, air thickened sauces. How do we know something is an air thickened sauce? What are some of the cues that something is an air thickened sauce? Exactly. You'll see the air. So step number 1, we'll see the air. It's going to be a chilled sauce. Chances are it is served cold unless there is a secondary thickener at play. And what makes whipped cream so stable? What molecule comes in and helps to whip cream to be so stable? Yeah, the fat molecules in the cream actually stabilize through resolubilization the air bubbles within the whipped cream. Any other questions or anything you're unsure of today? Great. I've read all of your proposals for your term paper, and I want to be very clear. When you write your term paper, what I'm looking for is for you to write 3 solid pages going in depth into a specific topic. So I need you to pick something that has enough science, first and foremost, that you can look up credible sources from journals, from peer-reviewed articles, from other scientists, not just the internet. And I also want you to be able to really deep dive and get into the history of whatever it is that you're exploring. So if you gave me a very broad general topic with many legs, I probably responded that you needed to narrow it down. If you're not sure, please use the Google Voice number to shoot me a text message so that we can discuss it. Or you can also email me, or you can write a message on Blackboard. You can respond to the discussion forum. There are lots of ways for us to communicate about this, but I want to make sure that everyone has a really great term paper. Are we clear on our term paper? Wonderful. Have a great day, and I'll see you for your next lecture, which is probably my favorite one, bread and cheese.